Hello everyone, my name is Yi Zhang and I'm a PhD student in Mechanical Engineering Department of Tufts University. So today I would like to present an ongoing research which is an augmented reality platform for introducing reinforcement learning to K-12 students with robots. So a brief introduction, I'm working in Tufts Center for Engineering Education at Outreach. We are an interdisciplinary center which our students, staff, and faculty collaborate on educational research, and we create educational tools and develop technology. My research is focusing on how we can demonstrate AI and introduce AI concepts to middle and high school students with educational robots. So one thing that motivates this research is we think it's important to teach K-12 students AI because AI is playing an increasingly important role in our daily lives. The video platform, the purchasing website, the social media that the kids are interacting a lot in their daily lives are all filled with many AI technologies. And also AI has impacted a lot of fields and industries and is predicted to be a critical tool in future work and careers. And also kids need to be aware of limitations of AI technologies and like privacy issues that is bringing by AI. So the reason we use AR to develop our virtual interface is because AR is strong at providing immersive experience and visualizing abstract concepts in physical world. And also compared to virtual reality, is easier to be implemented on different mobile platforms. And also AR has positively contributed to some K-12 education research and HRI research. So most current K-12 AI learning platforms like Cognitive Machine Learning for Kids are mainly designed in the virtual world. So the virtual world has some advantages like it's easy for students to access and it's easy to demonstrate abstract concepts. But what we want is to combine the virtual platform and the physical robots to leverage the advantage of a virtual platform and also to give students a more interactive and engaging learning experience. Also, we think by solving real-world problem with AI, they could not only learn what AI is, but also better understand how AI is applied in our world and is impacting our world. So a brief introduction to the reinforcement learning stuff used in our research. So reinforcement learning is the training of machine learning models to make a sequence of actions that could maximize environmental reward. Researchers have used reinforcement learning to train agents that plays Go or chess against the professional players, or train the robot to manipulate complicated tasks. So in reinforcement learning, the environment is represented as a Markov decision process, whereas it's a discrete set of states. A is a set of actions, T is a transition function that maps the probability of moving to a new state with chosen action and current state. R, it gives the reward of taking an action in a given state, and gamma is the discount factor. So the goal of a reinforcement agent is to learn an optimal policy that maximizes the long-term expected sum of discounted reward. So one way to learn the optimal policy is to learn the optimal action value function Q, which gives the expected sum of discounted reward for taking action A in state S. A commonly used algorithm to learn the Q function is Q-learning. In this algorithm, the Q function is initialized arbitrarily, for example, like all zeros. And upon performing action in state S, observing reward R and ending up in state X prime, the Q function is updated using the following rule, which alpha is the learning rate. And the agent is usually trained with epsilon gradient policy, which means it has the epsilon possibility to choose a random action to explore the environment and has a 1 minus epsilon possibility to choose the action with highest Q value based on its current learning experience. So the robot platform we used for our research is Lego Spec Prime. It comes with different sensors and bricks, and which allows the students to build and design and customize their own robot cars. And also it's programmable with MicroPython and Scratch-like block coding. And it has been used by K-12 education researchers and has proved to be a good tool to increase the engagement of learning experience. But one drawback of this robot is does not support Wi-Fi. So to solve the Wi-Fi limitation, we use the ESP8266 board as a Wi-Fi dongle to provide the robot wireless communication capability. This diagram shows how the communication part works. We developed a HTTP server on the ESP8266 board, which could send and receive HTTP requests. And the ESP board is connected to one of the sensor ports to the robot and could send data through UART. So if the users want to send a command to the robot, they could interact with the AR application. Then the AR application would send the HTTP request to the ESP board, and ESP board will fetch the data and send it to the robot through UART. And you can also do that on the other way, which means the robot will send data back to the AR application, which could be visualized by the users. So the tools we used for design our AR interface is Unity and Vuforia. So here is an image shows the physical environment of our activity, which is a robot moving in a 3x3 grid, and there's a image target for AR application to track. And here you can show there's an AR app running in a tablet. So the Unity is a powerful 3D and 2D game engine and the cross-platform IDE for developers. Euphoria is a popular tool for creating AR applications. So through combining these two platforms, we were able to develop interesting and immersive AR games or activities on different mobile platforms like iOS or Android. So based on all the components we have, we designed this treasure hunting game in a 3x3 grid world as a starting point to explore the role of AR and robot in K-12 AI learning. So the goal of this activity is to train the robot to move to find the treasure and go to the exit in a shortest route. We chose reinforcement learning as the AI learning concepts because it's the same to our nature of cognition of learning and is easy to be demonstrated on games that is running with a robot. So to help students understand the reinforcement learning training process and the concepts behind the activity, we designed this AR user interface with Unity and Vuforia. So in top of the UI, you can see there are key reinforcement learning parameters like state, action, reward, episode. And score is a gamification of the accumulated reward in current episode. So on the left side, you can choose what to show in the middle grid, which we will talk more about it later. And you can also tweak epsilon with the slider here. And then in the middle, it shows the virtual maze, which you can see there are treasures, exit, and two walls, which the robot could not pass. And on the right side is the manual training section. We want students to be able to perform some human-in-the-loop training to better understand how human can be part of the training process. And in the middle of it is a button to switch between automatic and manual training mode. When in manual training mode, the users will be able to manually give the robot reward to its last action with the slider below, and to help the robot select its next action by moving the robot in physical world and facing the robot to the desired direction. We have an image target attached to the robot to determine its position and direction. And on top right corner is an animation that shows a step-by-step reinforcement learning training process. For example, when the robot is waiting for you to tell it what's the next action, this chose action part will be highlighted as well as the action part here. And after you give it action, it will get a reward by users or the environment, and this part will be highlighted, and the reward here is also highlighted and will be updated. So we want to break it down the reinforcement learning training process to help students better understand how reinforcement learning works. And to make it not too overwhelming to see all of the information at the same time, we have these three buttons that the students will use to fold and unfold each of the section in the UI. So there are three different information you can show in the middle grade. So the first thing is learning experience, which is an intuitive visualization of Qtable. We think it's a little bit too overwhelming to show numbers to the students. So instead, we chose to use arrows and colors to demonstrate it. Each arrow shows a possible action in each state, and the color of the arrows is updating during the training process. When the color is greener, it means the robot thinks it's a good choice, and when the color is redder, it means the robot thinks it's a bad choice. And after you train in several episodes, it will be able to show a path here which demonstrates the robot's perception to the environment based on its current learning experience. And second thing you could show is how the state action pairs visited. It shows how many times each state action pair has been visited during the training. This provides a supplementary information when the students are doing human in the loop training, because it will show where the robot has not been visited and where the robot might need a little bit more training. So this could help the students to make a decision on giving the robot what's the next action and reward. And the third thing you could show is a past trajectory, which is an animation of robot's trajectory in a past episode. So through playing with this activity, we want students to learn about key reinforcement learning concepts like reward, action, state, etc. And also we want them to have the ability to connect the Q table with robots' decision making, and also to understand the trade-off between exploration and exploitation in reinforcement learning contexts. Also to understand the training process and how human can be part of it and impact the training process. To conclude, in this research, we designed an AI learning platform that combines the physical and the virtual world. And we designed a reinforcement learning activity based on this platform as a starting point to explore the role of AR and robot in K-12 AI education. And we also think it's a good approach for establishing common ground between a learning robot and a human user without requiring users a lot of mental rotations from a virtual interface to what is happening on the robot in the physical world, which we think it would benefit human-robot interaction. In the future, we are planning for a pilot study with high school students. We will evaluate their learning outcome, engagement, and other aspects, and also get feedback to improve our platform. Previously, we have done research which we designed a curriculum that contains 2 robot activity and 1 online activity to help them learn reinforcement learning. And we tested with some high school students. So in the future pilot study, we would like to utilize this platform and separate students into 2 groups to play with AR interface or the online platform, so we can better assess how AR could impact the learning experience. And during designing and the testing process, we found there are still some limitations that could be improved. For example, we found it might be a little bit too overwhelming to show everything in a single activity, and also reinforcement problem is too simple to be solved with human instruction. So we are designing a multi-level game to solve these problems and better leverage the power of robot and AI in education. On the other side, we're also trying to develop new modes for human-in-the-loop training that could leverage AR, which is to benefit the human-robot interaction aspect. So in the end, I would like to thank LEGO Education, PDC, and the Verizon Foundation for their supporting on this project. Thanks for your listening, and I'm looking forward to answering all your questions.